Look at this! A floating crane sitting in open water, lifting this massive structure clear out of the sea. The salvage weighs thousands of tons and the crane is floating. How is this possible? How does a floating platform lift something that heavy without tipping over and capsizing? Start with what's holding everything up: the pontoon. This is a massive, flat-bottomed barge, and it's not just big for deck space. It's big because it needs to displace an enormous amount of water. Remember Archimedes' principle. A floating object displaces water equal to its weight. The pontoon has to displace enough water to support the crane, the ship being lifted, and everything else on board. But size alone isn't enough. The pontoon is also extremely wide, much wider than it is tall. That width creates stability. The wider the base, the harder it is to tip over. It's the same reason a canoe flips easily, but an aircraft carrier doesn't. In stability terms, this is called metacentric height. The higher it is, the more the vessel resists rolling. A wide, flat hull gives you a high metacentric height, which is exactly why crane barges are built with a very high width-to-depth ratio. So, the pontoon does two things at once. It provides buoyancy to stay afloat, and it resists tipping with sheer width. And that's before anything has been lifted. The moment the crane takes weight, a new problem appears. When the crane lifts a ship on one side, all that weight shifts to that side. Physics says the platform should tip immediately, but it doesn't. Why is that? Well, it's because on the opposite side of the crane, there's a massive counterweight. Think of it like a seesaw. If you have equal weight on both sides, the seesaw stays balanced. The counterweight does the same thing, balancing the lifted load on the opposite side and preventing the platform from tipping toward the crane. The counterweight isn't small. It can weigh as much as the ship being lifted, and it's positioned as far from the crane as possible to maximize leverage. It's there from the start, before anything is in the water, before cables go taut. But there's still a problem. As the ship rises out of the water, the weight distribution changes. When the ship is still in the water, buoyancy is supporting some of its weight. As it lifts clear, that buoyancy disappears and the full weight transfers to the crane. The platform starts to tilt, just slightly, a few degrees to one side. That's where the ballast system comes in. Underneath the pontoon, hidden in the hull, are ballast tanks. Multiple tanks positioned throughout the vessel. These tanks are filled with seawater, thousands of tons of it. Hydraulic pumps can move water between these tanks, and they do it while the lift is happening. If the platform starts listing to port, water gets pumped from the port tanks to the starboard tanks, and the platform levels out. If the bow dips, water moves aft. If the stern dips, water moves forward. This ballast system is what turns a static counterweight into active stabilization. The crane structure itself is the last piece, the twin A-frames. You'll notice that there are two massive frames, one forward and one aft. These are called shear legs, A-frames made from tubular or truss-like structural members. They're not just there for strength, they're able to spread the load. If all the lifting force went through a single point, it would create a stress concentration. The pontoon's hull would have to be reinforced at that one spot, making it heavier and more expensive. But by using two A-frames, the load can be distributed across a wider section of the pontoon. The force spreads out, which means the hull can be lighter and still handle all that weight. The area beneath the crane foundations, the deck plating, is the most critical part. It's heavily reinforced with thicker steel and additional stiffening because this is where all that load gets absorbed and transmitted into the hull. The cables run from the top of both frames down to the ship being lifted. And as the ship rises, both frames share that load equally. It's the same principle as carrying a heavy box with two hands instead of one, spreading the load, reducing the stress. And here's how it actually runs. Before the lift begins, the crew sets the ballast. Water is distributed in the tanks to ensure the platform is level and stable. The counterweight is in position. The shear legs are lined up over the lifting point. Everything is checked. Then the hydraulic winches start. The cables go taut and the ship begins to rise. It's not fast. A lift like this can take hours, but speed isn't the goal. Control is. The ship clears the water and hangs in the air, suspended by the cables, and the platform stays perfectly level. So, that's how floating cranes manage to lift entire ships without capsizing. The wide hull resists tipping, the counterweight creates balance, the ballast compensates for shifting weight, and the twin frames spread the load. If you take away any one of those, the whole system falls apart. But when they all work together, you can lift thousands of tons while floating in open water. Hopefully you've enjoyed this video. If you want more content like this, please be sure to subscribe. Until next time, thank you for watching.